In the last screencast, we discussed how a rigid body is defined, and in particular, we talked about how the center of mass, and knowing where the center of mass is, can help us apply some of the findings we've already developed for multi-particle systems. And so this is true for the translational kinetics of a rigid body. And so what we see is that if we take the center of mass of a rigid body, then we can apply Oilless First Law. Now, Euler was the first person to apply this idea to rigid bodies, and so that's why it's attributed to him. We'll then talk about Euler's second law later on, which is rotational. So Euler's first law simply states that F equals ma. We've seen this before, but now notice that we're saying that F sub g, which is the total of all the external forces that are applied to a rigid body, are equal to the total mass of the rigid body, and we're simply multiplying that times the acceleration of the center of mass as observed in the inertial reference frame. And so we've done this all the time. We've done this many times with multi-particle systems. We do this with single particles, and here this will be one of our equations that we can solve to develop equations of motion as well as constraint equations. Now, the simplest way to think about this is in projectile motion. And in projectile motion, we're saying that the acceleration is only due to a uniform gravitational field. So it's always pointing in the Earth's direction. And in that uniform gravitational field, let's say we have our rigid body here, and we toss our rigid body, then the center of mass of the rigid body is going to travel in a parabolic curve, just like a normal projectile motion. Now, that's completely separated, because recall that we talked about separation of angular momentum, and from that we had a translational equation and we had a rotational equation, and so that's completely separated from any rotation that the rigid body might do. So if we toss it and we rotate it at the same time, it's going to rotate through the air, but the center of mass itself is going to travel in a parabolic arc no matter what type of rotation is occurring. And so we see in this situation that Euler's first law, when we apply this, gives us the equation of motion for the system. Now, in other situations where we have rolling that occurs or other constraints that change the motion of the system, then Euler's first law is going to be one of three equations, because we have 3 degrees of freedom. And the equations of motion themselves are going to be coupled, and it's going to help us find constraints as well as the equations of motion. Now, so far we've predicated this entire discussion on knowing where the center of mass is in a rigid body. However, we haven't actually done that yet ourselves. So let's start out with a multi-particle system. And in our multi-particle system, we have that the center of mass location, so this is g with respect to O, is equal to 1 divided by the total mass of the system multiplied by this discrete variable where we add up the mass multiplied times its position vector, and then that gives us our location of the center of mass with respect to O. Now, in a rigid body, we need to come up with a continuous definition, and this is shown here. And what we've done is we've kept our mass of the entire rigid body, we're calling it m sub g, and then we've replaced our discrete addition with an integral across the entire body. Now, we're integrating across an element dm, and an element dm is simply going to be a volumetric element in which we can apply a density or a mass distribution within that element. And so also notice here that we've kept our term, which is our position vector, and our position vector, which is dm with respect to O. And so here the position vector to this element dm would be this vector as we see here. And then our integral is a volumetric integral. So we're adding the continuous elements dm throughout the entire body. And so this is volumetric, but we're in planar motion, so it'll end up being an area multiplied times a density with the appropriate units. And so we can replace dm, the differential mass, by our density. And so dm is equal to our density multiplied times the differential volume. And so dm being rho dv, and this allows us to set up our integral now, instead of as a mass, but now we can set up our integral in terms of the geometry of the rigid body itself. And one other thing to point out is that in our density can vary throughout the rigid body. And because the density can vary throughout the rigid body, it wouldn't be uniform, we can make our density a function of the position of the differential mass. So as this differential mass changes throughout the rigid body, the density can change as well. And so we end up with our final expression in which we can calculate the center of mass for a continuous body. So the position of G with respect to O is going to be 1 divided by the entire mass of the body, and then we're going to integrate over the entire body of the position vector of each differential mass, multiply it times the density, and the density can be a function of that location, and then we're integrating over the volume of the body, so we'll turn this into a geometric integral. To demonstrate how to compute the location of the center of mass, we're going to use an example which you probably saw in statics at some point. This is a classic example where we're finding the centroid of a triangle, but here we're going to compute the center of mass location, and we're saying that the triangle here has a uniform density and a constant thickness. So this sets us up well for planar motion. So first, write out the formula that we have for calculating the center of mass, location of the center of mass for a continuous mass body. And the first thing that we see is that what's defined in the problem is a uniform density. So instead of having rho as a function of the location of our differential element, this will simply be rho. And now we need to take each of these terms and apply what we know about the system and what's given us in our geometry. So what you want to do is draw a differential mass, or draw a differential volume rather, on your drawing. And so the differential volume itself is going to have an x position and it's going to have a y position. So that means that the vector, the position vector to that differential element will be r of dm with respect to O, and it's going to have an x position in the b1 direction, and it's going to have a y position in the b2 direction. So here's our x position, and then here's our y dimension for the differential volume and the differential element. Now we see here that the units of our density are in mass per length squared. And so if they're in mass per length squared, then dV is going to have units of length squared, because rho times dV should give us the mass, which should be in kilograms. And so if dV, as we've drawn it here, also is equal to dx multiplied times dy. So now we've taken care of our uniform density. We're going to replace dV with dx dy, and now we have our position vector of x in the b1 direction and y in the b2 direction, which will go into this position vector. We have our mass, and now we need to define the bounds on our integral. So with dx dy, this is going to be a double integral, so we need to find bounds on x and bounds on y. So let's first look in the b2 direction, which are our bounds on our y. And we see that the lower bound is 0, and then the upper bound, we're going to be constrained by the top of this triangle. And so the upper bound is going to be h minus h over w multiplied by x. And now with our upper bound defined in terms of x, when we look at our x bounds, or what's in the b1 direction, we can see that we're constrained by 0, and then we're constrained by w, because when we put in w at x, we're going to have this position, and then we have 0 at x, we're going to have our h. So our bounds for in the b1 direction will be 0 to the length w. So now set up the entire integral, where the position of the center of mass with respect to O will be a double integral, 1 divided by the mass, multiplied times a double integral, and then we're going to put our position vector to the differential mass on the inside. So this will be x in the b1 direction plus y in the B2 direction. So we're using Cartesian coordinates here. And it should point out that you can use polar coordinates when necessary, and there's an example in the book that uses that. And then this is rho. And then we're going to put dy on the inside because we've defined our bound for y in terms of x. So that means we want to evaluate it first and then apply our x bound. So put dy on the inside, so we evaluate it first, dx on the outside. And then for our bounds, our inner bound needs to correspond with dy. And so this will be from 0 to the expression h minus h over w multiplied times x. And then for the outer bound, which will be on the x bounds, this will be from 0 to w. So now we've set up our double integral to calculate the center of mass of the triangle. So to evaluate this, let's make it simpler. We can take out our density because it's a constant density, and we can also take the integral of each of these terms. So we'll take the integral of xb1, double integral of xb1, plus the integral of yb2. And so now we have integrals in which we'll get a scalar in the b1 direction and then a scalar in the b2 direction, which will give us the center of mass. So if we look at the b1 term and integrate the inner integral, then we still have left a 0 to w of x h minus h divided by w times x dx, and we've evaluated with respect to y, and so this is in the b1 direction. And then evaluate the integral that's still left in the term, and we get rho over m, and it's h w squared divided by 2 minus h w squared divided by 3, and this is all in the b1 direction. And then this term we can reduce to rho divided by m of h w squared divided by 6. And so that's our b1 term. And so now we evaluate the second double integral, which is in the b2 direction. And so when we integrate the inner integral, which is with respect to y, we get rho over m. We have to retain our integral from 0 to w, and then this is 1/2 multiplied times h squared minus 2 h over w x plus the quantity h squared over w squared x squared dx in the b2 direction. So now we have one integral left to evaluate in the double integral, and so we get rho over m multiplied times 1/2, and it's h squared w minus 2 h over w multiplied times w squared over 2 plus h squared over w squared multiplied times w cubed over 3. We have lots of terms that cancel, and we collect our terms, and then this is equal to rho over m h squared w over 6 in the b2 direction. So now we have both of the components for the center of mass location. And in this expression we still have one more step to go. And this is a departure from what you learned in statics about finding centroids, because now we're finding the center of mass. You can see that we still have the terms left in here of rho and our mass, so our density and our mass, and they have a relationship that we need to take advantage of. And that relationship is that the mass of the entire rigid body is equal to rho multiplied times the volume. And the reason why we can give this expression is because the density is constant. So it's the density multiplied times the volume will give us the mass. And so here, our volume is the area of a triangle. And so this is 1/2 base times height. So it's 1/2 multiplied times the base, which is w, and then the height of the triangle is h. This is true for any triangle, not just a right triangle. And so this gives us the expression we can substitute, which is that the mass is equal to rho W times h divided by 2. And so now we substitute this relationship into our current expression for the location of the center of mass, and then finally we're going to get the location of the center of mass with respect to O is equal to W over 3 in the B1 direction plus h over 3 in the B2 direction. So this should correspond with what you know or what you can look up in a table for the location of the center or the centroid, which is going to be 1/3. So we'll just say that's B over 3 if there's a base, and then h over 3 if the total height is an h. And so this should make sense. But now notice our coordinates here, or notice that what basis we've expressed this in. We've put this into the B1 and B2 basis. And it's really important to put this in the B1 and B2 basis instead of an inertial basis, because we're going to take these objects and we're going to throw them, we're going to roll them, we're going to spin them. And so, as you have found out before about kinematics, it's important to express things oftentimes in the basis that's fixed to the body because the expressions are much simpler. If we express this in an inertial basis and once it begins to move, now we have lots of sines and cosines and lots of trigonometry and angles and angular velocities and so forth that we have to deal with. So to sum up, we've calculated the location of the center of mass, and we've done this in the body frame. This has looked a whole lot like what you've calculated for centroids in statics, except now we need to relate the mass and the density. These are new concepts because now we'll be dealing with inertia. And to do that, that then gives you the expression in terms of the geometry of the system, which is going to be a length in one direction and a length in another direction. It's also, as we mentioned, important to put this into the body frame.